Okay, this is lesson 3, week of April 20 through the 24th. And this is entitled Lenz's Law. It's actually section 25.2. We have 2 lessons in 25.2, and then that will finish us up with the chapter 25, and then we'll do a test on 24 and 25. The title of today's lessons is Lenz's Law. Lenz's law is very interesting. It's going to become actually pretty important for us. We've already now talked about how an electric current through a wire will create a magnetic field, and then that a magnetic field can be used to create electricity. And because of that, we can put together something called a generator, which we talked about last time, an AC generator. Simply take and spin a wire, a coil, a magnet inside of a coil of wires. Whoops, drop that. Hopefully it's still working. Spin that coil inside of there, and we'll get that to light up. That's because that magnet right there is spinning around, cutting perpendicular to the magnetic field. We can also do it in reverse. We could put wires inside of a magnetic field and spin those. So that we've already covered. Now, here's what Lenz's law says. Let's say I have this coil of wire. Now let's say there's a light bulb here. It doesn't make any difference. If I take this and either move the magnet or move the coil, either way, we would say we have a changing magnetic field. The magnetic field is cutting across the wires. When it does that, it creates a current. But now I want to take you back to the third right-hand rule. Let's say the current in here is this direction. Well, I'll do it this way. This direction. Then this becomes a magnet itself. When I put this wire through, this magnet through, that causes a current in here, which becomes a magnet. Now the question is, what direction is the magnetic field? And that's what Lenz's law says. Lenz's law says that the direction of the current induced in a conductor, that's this wire, so I take and I put this through, caused by a changing magnetic field, is such that the magnetic field created by the current opposes the initial magnetic field. In other words, when I push this through, I'm creating a magnet, and the magnet that's inside of here that's being created is in the opposite direction of this one. In other words, they're going to push away from each other. That is Lenz's law. So when I create this current, I also create a magnet, and by creating the magnet, I now have, like if I had a second magnet that opposed this one. Let me see if I have a magnet here. So if in a sense, I can think of it this way. If this magnetic field pushes away from it, as I was pushing in, this becomes a magnet. And I don't know if you can see that, but they're pushing away from each other. If I let it go, they will push away from each other. So that is called Lenz's law. Lenz's law, I have a number of fairly good demonstrations, but they're at school. And so I have a video I'm going to have you watch. What's interesting is you do need a coil of wire, and you do need a changing magnetic field. And I want to stress this before we go further. In other words, as long as this is moving through, I'm creating, or I have a changing magnetic field. As long as this is moving through, the magnetic field is changing. But if I just take and stick this magnet right there and stop, the magnetic field is no longer changing. As a result, there will be no current, and so there will be no magnet that's produced in here. So there's nothing happening right now, but as soon as I pull this out, I create a magnetic field that will be pushing against this one. As soon as I go this way, I create a magnetic field that's pushing against this one. So there has to be a changing magnetic field. Now, here's what's interesting. If I take a single coil of wire, like this one, or this one, And now just think about this. I run an electrical current through here. What does that do? Well, that creates a magnetic field. When that is starting up, in other words, I put a current in here and that current builds up. It doesn't start out, it's like water in a stream. It starts and it builds up. As it is building up, that is creating a changing magnetic field, which causes there to be an opposing magnetic field, which actually tries to force current back the other direction. All right, let me say that again, because that's a little bit funny. I send current through here. That creates a magnetic field. That magnetic field is changing because the current is just starting through the wire. And at that exact time then, a magnet is produced, a changing magnetic field is occurring, which is going to cause current to try and flow backwards in here. We call that a back EMF. You've experienced this perhaps when you have an electric motor and you start to spin that motor. The minute that motor starts to spin, those coils are creating a magnetic field that the coils are in, and it tries to force current backwards. If you've ever been at home, some of you may not know this, but when you hear your refrigerator kick on, in a lot of houses, especially older houses, when that refrigerator kicks on, you'll see the lights dim slightly in the house. And that's because it takes 110 volts to start that motor. That motor, the current drops. There's a back EMF, and it actually causes the voltage to drop. And you'll see if anything else on that circuit will actually dim just a little bit because the voltage has dropped. We'll talk about that a little bit in your book. One of the things that happens is that anytime I have a coil of wire, it actually works as a resistor if I have alternating current which is going back and forth. Because when the current goes back and forth, we have a changing magnetic field. And that coil of wire then acts as a resistance to that happening. And that is actually called an inductor. Joseph Henry, the one who came up with the same idea of an alternating current generator at the same time that Faraday did, the unit that he is credited with is for the inductor because it's in the same family. So I wanted to show you something. I have here, let me just bring this up so you can see it. This is a piece of metal, and these are plastic. There's a reason for that. It's actually rubber. This is to make it safer. I've put a little piece of orange tape on here. And what I have in here, let me bring this up a little bit so you can see it. You see the coil of wires down here. And this is a big iron bar. And what I'm going to do in a second, in fact, I'll do it right now. You can barely hear it when I do this. In fact, I don't know if you can see it, but my lights dim in this room when I do that. I'm getting a back EMF when I do it. I am creating an electromagnet. That electromagnet, by the way, this will only let me turn it on for just a fraction of a second. I don't know if you can hear it. And what's actually happening is the current is changing. Even though this is only on for maybe a half a second, this is causing this coil of wires to become an electromagnet. So if the current is going this way, it's an electromagnet. But then every 60 times every second, the direction of the current switches. So now it switches this direction, and then it goes this way. So there is a magnetic field which is switching back and forth. It's very similar to this, where this magnet inside of here is spinning back and forth 60 times every second, or however many times every second that I spin it. So now what's going to happen is this. This is a coil of wires. You say, no, it's just a piece of metal, but a piece of metal is a big coil of wire. So when I put this on and push it, and this is going to be real hard for you guys to see, but watch the orange here. Okay, I don't know if you saw that, but it's on the ground now. I'll do it again. I wish I could show you this better. All right, I'm going to say when I push it, 1, 2, 3. Then it goes shooting off. What's happening is this magnet is going back and forth. This current is then switching back and forth. So the current is going this way, then this way, then this way. And as a result, this is becoming a magnet, but it will always be a magnet that is opposing the direction of the current. I mean, of the magnetic field that's doing it. So I'm going to put my hand here, and maybe you can see it a little bit better. Now, I have a second piece of metal here without the rubber on top. Let me put that on. Okay, watch carefully. Okay, obviously nothing happened. Why did nothing happen? Well, the answer has to do with that right there. This is not a complete coil of wire. So I am creating a magnet, but there's no current flowing in here, so this doesn't become a magnet. Now, just to demonstrate this so you understand it a little bit better, I have one last thing. I have a light bulb that is connected up to actually a fairly small coil of wires, but it is connected. When I put this on and I turn this on, I'm going to have a magnetic field. This is going to be opposing, but it turns out that there's so little current flowing through here that there's hardly any magnetic field. Remember, it depends upon the length of the wire, and the length of the wire actually will determine how strong the magnetic field is. But watch what happens when I turn it on. Let me move that way. All right. That light bulb lights up. In fact, I'll bring it a little bit closer so you can see it. There's the light bulb right there. And it turns on. That's because there is a current which is flowing through here. So this is causing a current to flow. I should have done that one first. In here, no current is flowing. And this is a piece of aluminum, actually, so it doesn't become magnetic at all. But when I put that one on, bring it up a little bit closer, maybe you can see it take off a little bit better. It goes really fast. Yeah, almost too fast to pick up on the video. So maybe I'll do it this way, and we'll shoot it across the room. No, you can hardly see it. It's a shame. This is where we're missing something. There's actually 2 other Lenz's law demonstrations I would normally do at school, but I can't really even show them to you here. One of them you have to see for yourself. It's the coolest demonstration. You take a copper pipe, and I drop neodymium, the strongest magnet I have, down through that pipe. And of course, copper is not magnetic. And yet that magnet just barely floats down. It's like it just drops real slowly. And that's because as it's falling, it is creating a current in the copper pipe, which is causing the copper pipe to become a magnet, which is trying to oppose it. And it falls just at the right speed where gravity and the magnetic field are balanced, and it drops at a constant velocity. It's very similar to a terminal velocity for a parachutist when he jumps out of an airplane and puts his arms out and eventually reaches a point where the pull of gravity down is the same as the push up. But there are so many good Lenz's law demonstrations that I have a YouTube video that I want you to watch. And as part of the discussion that'll go with it, there's no homework from the book other than to read through section 25.2. I want you to mention at least 3 of the demonstrations that he does. He does several of them. And it's pretty cool, the things that he does. He's going to be working with plates of copper, but one thing you have to understand is that if this is a plate of copper, and I bring a magnet and I move the magnet along there, that magnet is going to create currents in the copper, right where the changing magnetic field is. And so you're going to see that. He's going to actually take a piece of copper. I know this isn't a piece of copper, but he's going to take a piece of copper and he's going to, for instance, drop a magnet at it. And it actually, as it gets closer, it starts creating currents in the copper right there, which then oppose the magnet, and you'll watch what happens when that takes place. So that is, that's section 25.2, the first part, Lenz's law. And so with that, we'll end, and then we have one more section that we need to do yet.